Try to imagine nothing. Go ahead. Close your eyes and try to visualize absolute emptiness. You probably see a black void, maybe some stars in the distance if you're feeling romantic. But essentially, you picture a vacuum. You think of space as a stage, a big empty box where stuff happens. You put a planet here, a star there, maybe a confused astronaut floating in the middle. But the space itself, to you, it's just the container. It's the absence of things. I hate to break it to you, but that container doesn't exist. The idea of empty space is the greatest hallucination of the human mind. The universe isn't a box, it's a glob of jello. Okay, maybe not literal lime-flavored gelatin, but physically speaking, you are walking through a medium that is constantly being twisted, squashed, and pulled. When you look at the air in front of you, or the vacuum of space, you aren't looking at nothing. You are looking at a field. And until you understand what a field is, you don't understand physics. You're just memorizing rules for a game you don't know how to play. Let's start with something you can actually touch. Imagine a big, wobbling block of elastic material, a giant cube of jello sitting on a table. Now, suppose I reach in, grab a tiny speck of dirt trapped inside that jello, and I pull it. The jello distorts. It stretches. If you want to describe what happened to that block, you can't just say it moved. That's lazy. You have to describe how every single point inside that block shifted relative to every other point. We call this strain. If I pull the corner, the middle moves a little. The far side moves barely at all, and the point under my finger moves a lot. To describe this mess, we need numbers, a lot of numbers. For every tiny point in that jello, we need to know how much it stretched in the X direction, the Y direction, and the Z direction. And it gets worse. We need to know if it twisted. Did the top slide right while the bottom slid left? That's a shear. Suddenly, this innocent block of jello is a mathematical nightmare. To fully describe the stress and strain inside it, we can't just use a single arrow. We need a tensor, a beast of a mathematical object that packages all these stretches and twists together. But here's the beautiful part. This isn't just about jello. This is how the entire universe works. Physics is the business of assigning numbers to points in space. That's it. That's the job. If you assign a single number to every point in space, like, say, the temperature, you have a scalar field. Imagine a block of metal that's hot on one side and cold on the other. You can close your eyes and point to any spot inside that metal, and there is a specific number waiting for you, 20 degrees. Move an inch left, 25 degrees. The temperature doesn't jump around randomly, it changes smoothly. It forms a landscape. Now, imagine drawing lines connecting all the points that have the exact same temperature. You get these invisible surfaces, like the contour lines on a topographic map. We call them isotherms. They are imaginary, but they tell you the shape of the heat. But a single number isn't enough for the interesting stuff. Sometimes, the universe has an arrow at every point. Think about a rotating object, or water flowing in a river. At every single point in that river, the water has a speed, but it also has a direction. It's going somewhere. You can't just say, the water is moving at 5 miles per hour. You have to say, 5 miles per hour downstream. This is a vector field. Imagine the room you are sitting in right now. The air seems still, but it isn't. There are tiny currents everywhere. If you could freeze time and attach a tiny little red arrow to every molecule of air showing where it was going, the room would look like a porcupine. That forest of arrows is a field. Heat flow works the same way. Heat doesn't just sit there, it flows from the hot spots to the cold spots. So, superimposed over your scalar field of temperature numbers, there is a vector field of heat flow arrows. And here is the rule. The heat arrow always points downhill. It wants to get away from the hot zone as fast as possible. Now, we need a way to connect these two things, the temperature numbers and the flow arrows. How do we find out which way the heat will flow just by looking at the temperature map? We use a mathematical machine. We call it DEL, or Nabla, which is just a fancy name for an upside-down triangle symbol. But think of it as a meat grinder for function. You feed it the scalar field, the map of temperatures, and it chews it up and spits out a vector field. This operation is called the gradient, and it is exactly what it sounds like. If you are standing on a hillside in the pitch dark, and you want to know which way is up, you feel around with your feet. You find the direction where the slope is steepest. That direction is the gradient. The gradient of the temperature field is a vector that points in the direction of the hottest change. It tells you, if you want to get hotter, go that way. And the heat flow? It simply obeys the opposite of the gradient. It runs down the hill. But nature isn't satisfied with just flowing down hills. Sometimes nature likes to spin. Imagine you have a vector field that looks like a whirlpool. The arrows aren't flowing out from a center, they are circling around it. If you drop the leaf in there, it wouldn't just move, it would rotate. To measure this swirliness, we use another operation called the curl. If the gradient measures the slope of the hill, the curl measures how much the field is twisting. It tells you the rotation. And then there's the divergence. This measures how much the stuff is spreading out. If you have a nozzle spraying water, the divergence is high at the nozzle because water is exploding outward. If you have a drain, the divergence is negative because water is vanishing into it. Why am I telling you about hills, swirls, and drains? Because these three concepts, gradient, curl, and divergence, are the language of reality. Maxwell's equations, the laws that govern light, electricity, and your cell phone, are just sentences written in this language. They say things like, the divergence of the electric field is the charge. Electric charge is a sprayer that shoots electric field arrows outward. Or, the divergence of the magnetic field is zero. There are no magnetic sprayers, no magnetic charges. Magnetic lines never start or stop. They just loop forever. Speaking of magnetism, this is where things get really weird. You think you know what magnetism is. You played with magnets as a kid. You know they stick to the fridge and hate each other if you flip them around. But have you ever asked why? Why does a wire carrying an electric current suddenly turn into a magnet? Let's look at the Lorentz force. It's the rule that says if you shoot a charged particle through a magnetic field, it gets pushed sideways. Not forward, not backward, sideways. It's a force that acts perpendicular to the motion. That's bizarre. Gravity pulls you down. Electrical attraction pulls you closer. But magnetism pushes you sideways, like a rude pedestrian shoving you into traffic. The standard explanation involves the right-hand rule. You hold up your hand, point your thumb, curl your fingers, and look like you're trying to hail a taxi while doing yoga. It works, but it's arbitrary. Nature doesn't have hands. Here is the truth. Magnetism is not a separate thing. It's just electricity seen from a moving perspective. Imagine a copper wire. Inside, you have positive copper ions fixed in place and a sea of negative electrons flowing through them like a river. This is the current. Now imagine a single negative charge moving alongside this wire at the exact same speed as the electrons inside the wire. From your perspective, standing still in the lab, you see a current. You check your rule book and it says, currents create magnetic fields. Okay. The magnetic field pushes the moving charge toward the wire. Simple. But wait. Let's look at it from the perspective of the moving charge. If you are the charge, you are looking at the electrons in the wire, and they look stationary relative to you because you're moving at the same speed. If they are stationary, there is no current. If there is no current, there is no magnetic field. So if there is no magnetic field, the force disappears, right? The charge should drift away? Wrong. The charge still gets pushed toward the wire. But how? If the magnetic force vanished, what is pushing it? Einstein steps in. You see, when things move, space itself contracts. It squishes. This is special relativity. From the perspective of our moving charge, the positive ions in the wire, which were stationary in the lab, are now rushing backward. Because they are moving, the distance between them shrinks. They get packed denser. Meanwhile, the electrons in the wire, which are moving with us, appear stationary. Their spacing relaxes. They spread out. Do you see what just happened? The wire, which used to be electrically neutral, now has a higher density of positive charges and a lower density of negative charges. To the moving particle, the wire has suddenly become positively charged. It's not magnetism pulling the particle in. It's good old-fashioned electric attraction. The particle sees a positively charged wire and wants to hug it. So what we call a magnetic field in the lab is just an electric field disguised by relativity. It's what happens to electricity when you start moving. This connects back to our vector field. We said earlier that fields define the force on a charge. We have an electric field vector, E, and a magnetic field vector, B. What we just discovered is that E and B aren't two different actors. They are the same actor, changing costumes depending on how fast you run past the stage. If you stand still, you see E. If you run, you see a mix of E and B. They are components of one giant four-dimensional object, the electromagnetic field. But there is a catch. To make this work, charge has to be indestructible. Think about the equation of continuity. It's a fancy way of saying charge is conserved. You can't create electrons out of nothing, and you can't make them vanish. If a current flows out of a box, the amount of charge inside the box must go down. It's basically accounting. If charge wasn't conserved, if it could change depending on your speed, the whole universe would break. Imagine heating up a block of metal. The electrons speed up. If their charge changed because of that speed, the block would suddenly become electrically charged just because it got hot. Massive sparks would fly every time you made toast. Since your toaster doesn't kill you, usually, we know charge is an invariant scalar. It's the same number no matter how fast you go. Now, let's go back to those magnetic field lines. Remember, divergence of B is 0. No magnetic charges. This means magnetic field lines have to form closed loops. They are like rubber bands that never break. If you have a straight wire, the field lines circle around it. If you have a loop of wire, the field lines thread through the middle and wrap around the outside, looking like a donut. This creates the magnetic dipole. It's the basic unit of magnetism. You don't have a north pole and a south pole sitting separately. You have a loop. The north is just the side where the lines come out, and the south is where they go in. But here is a question that should bother you. Where do the lines go when they hit the end of a bar magnet? They don't stop. They go through the magnet. A permanent magnet is just a solenoid that doesn't need a battery. Inside that iron bar, billions of tiny electrons are spinning. Each spinning electron is a tiny current loop. In iron, these loops decide to line up and sing in the same choir. The result is a macroscopic magnetic field. So there is no magic magnetic fluid inside the iron. It's just currents, permanent atomic currents that never stop flowing. But we are still describing this with lines and loops. Is that what's really there? Are there invisible spaghetti strings filling the room? Of course not. The lines are just a drawing tool. What's really there is the vector potential. And this is where we have to abandon the high school pictures entirely and look at the machinery under the floorboard. Because it turns out the magnetic field B might just be a derivative of something more fundamental, something we call A. We left off with a cliffhanger. We stripped away the magnetic field lines and realized they are just cartoons. We realized that magnetism and electricity are the same thing, just viewed from different speeds. But if we want to calculate this mess, if we want to actually predict what the universe will do next, we need to talk about the ghost in the machine. We need to talk about A. In electrostatics, life is easy. You have a scalar potential, voltage. It's like height on a topographic map. If you know the voltage everywhere, you just roll the ball down the hill, and that's your electric field. Simple.
But magnetism is a headache, because the magnetic field doesn't act like a hill. It acts like a whirlpool. It has a curl. So we can't represent it with a simple scalar number. We need a vector potential. We call it A. Think of A as the momentum of the field. If you have a flow of electric current, it drags the universe along with it. The current creates a river of this vector potential, flowing in the same direction. The magnetic field is just the swirl that happens around the edges of this flow. Now, is A real? Or is it just a mathematical trick to make our equations pretty? In classical physics, you can treat it as a trick. You can add any random value to A, and it doesn't change the physical magnetic field at all, just like changing sea level doesn't change the steepness of a mountain. But in more advanced physics, quantum mechanics, this ghost field turns out to be the main character. It's the thing that actually matters. If you don't like ghosts, you can do it the hard way. You can calculate the magnetic field directly from the currents using a beast of a formula called the Biot-Savart law. Imagine breaking a wire into infinite tiny pieces.
Each little piece of current screams out a magnetic command to the rest of the universe. The Biot-Savart law is just the sum of all those screams. It's a messy calculation involving cross products and inverse squares, but it tells us something profound. The field at any point is the sum of the influences of every moving charge in the universe, weighted by distance. This leads us to the dipole, the fundamental atom of magnetism. Since we can't have magnetic charges, the smallest magnetic object is a tiny loop of current. Far away from a complicated mess of wires, everything starts to look like a simple dipole. It doesn't matter if your current loop is a square, a circle, or a triangle. From a distance, the universe doesn't care about the shape. It only cares about the magnetic moment, the current times the area. This is why atoms, with their spinning electrons, behave like tiny bar magnets. They are microscopic loops. Now, I want to pivot. We've been talking about fields as if they are these ethereal, magical clouds. But to truly understand the vacuum, you need to think of it as a solid object. You need to think about Jell-O again. When we study the mechanics of solid materials, elasticity, we find the exact same mathematics that governs the vacuum of space. Consider a glob of Jell-O that is twisted and squashed. To describe the internal state of that Jell-O, we can't just say it's under pressure. Pressure is a scalar. It pushes everywhere equally. But in a solid, you can push on one face and pull on another. You can shear it. We describe this internal torture with a stress tensor. It's not a single number. It's a matrix of forces. It tells you the force in the x direction on the face perpendicular to the y-axis, and so on. And how does the material respond? It deforms. We call this strain. If a point inside the material moves, we describe that displacement with a vector. The strain isn't just the displacement, it's the change in displacement from one point to the next. It's the stretching and the twisting. This is defined by the strain tensor. This tensor has 6 independent numbers that tell you exactly how every patch of space is being warped. Why am I talking about Jell-O in a physics script? Because energy doesn't care what it's made of. When you squeeze a spring, you store energy. When you shear a block of metal, you store energy. The amount of energy stored depends on the product of the stress, how hard you push, and the strain, how much it moves. This is true for the vacuum of space, too. An electric field is a stress. A magnetic field is a stress. The empty space between stars is loaded with potential energy, stored in the electromagnetic fields just like energy is stored in a twisted rubber band.
If you understand Hooke's law, that stress is proportional to strain, you understand the basic machinery of existence. In a solid, if you kick it, a wave travels through it. We call it sound. The speed of that sound depends on how stiff the material is and how heavy it is. In the vacuum, if you kick the electromagnetic field, a wave travels through it. We call it light. The speed of light is determined by the stiffness of the vacuum, just like the speed of sound is determined by the stiffness of a rock. But here is where the analogy gets fun. Materials aren't perfect. If you pull a spring too hard, it snaps. If you take a piece of chalk and pull the ends, it breaks. But notice how it breaks. It snaps perpendicular to the pull. Why? Because chalk is weak in tension. It can't handle being pulled apart. But if you twist the chalk, it breaks in a spiral at a 45-degree angle. Why? Because twisting creates a shear, but that shear is mathematically equivalent to a tension at a 45-degree angle. The chalk still breaks in tension, but the geometry of the twist hides where the tension is. Nature is full of these hidden mechanisms. Materials like plastic film behave even stranger. You crumple it, and it slowly unfolds. It remembers its shape. It has internal viscosity, fluids moving between cells, that fights the restoration. The vacuum of space doesn't seem to have a breaking point or viscosity in the same way, but the math of tensors, the stress and the strain, is the language we use to describe gravity and the curvature of space-time itself. Einstein didn't invent a new language. He borrowed the language of geology and engineering. He treated the universe like a giant, bendable solid. So, what is the quantum vacuum? It is not empty space. It is a medium.
It is a playground of fields described by vectors, scalars, and tensors. It has a temperature field. It has a heat flow vector. It has electric and magnetic stresses. It has a vector potential that guides the flow of reality. Understanding physics isn't about memorizing the formula for the magnetic field of a solenoid. It's about having a feel for the field lines. It's about understanding that a differential equation isn't just algebra. It's a set of instructions for how the universe changes from 1 millimeter to the next. As Dirac said, you only understand an equation if you can guess the answer without solving it. You need to visualize the invisible. So, the next time you look at the night sky, don't see emptiness. See the fields. See the tensors stretching and squeezing. See the huge invisible ocean of vector potential swirling around every wire and every atom. The universe is a crowded place, my friends, and the nothing is the heaviest thing in it. If you enjoyed having your perception of reality twisted like a piece of chalk, hit that like button. Let me know in the comments if you want to dive deeper into the tensors that hold the universe together.
Space might be finite, a measurable volume, but it has no edge, no end in the way you're imagining it. Imagine a bug, a tiny flat bug living on the surface of a ball. This bug can only perceive 2 dimensions. It can move forward, backward, left, right, but it has no concept of up or down. For this bug, the surface of the ball is the entire universe. There's nothing else. Now, does this bug's universe have an edge? No. The bug can walk in any direction forever, and it will never hit a wall, never fall off, never reach a sign that says, end of space. But wait, is the bug's universe infinite? Also no. The surface of a ball has a definite size. It's measurable. It's finite. So how can something be finite but have no edge? Here's the secret. The surface curves. It wraps around. If the bug walks in a straight line long enough, it ends up exactly where it started, without ever turning around. The bug circumnavigates its entire universe just by going straight. Finite, but unbounded. Limited size, but no boundary. That's the key. Now here's where it gets interesting. The bug can actually discover that its space is curved, without ever leaving it. Without ever floating up into the 3rd dimension and looking down at the ball. The bug can figure it out from within. How? By doing geometry, by measuring things carefully. Now here's where it gets interesting. The bug can actually discover that its space is curved without ever leaving it, without ever floating up into the 3rd dimension and looking down at the ball. The bug can figure it out from within. How? By doing geometry, by measuring things carefully. Let me show you what I mean. On a flat surface, if you draw a triangle and measure all 3 angles, they always add up to exactly 180 degrees. Always. Every triangle. No exceptions. But on a curved surface like a sphere, the angles add up to more than 180 degrees. The triangle is fatter than it should be. On a flat surface, if you draw a circle and measure the circumference, it's always a little more than 6 times the radius. That's just how circles work. But on a sphere, the circumference is less than you'd expect. The surface curves, so the circle pinches. The bug can do these measurements. The bug can discover, through careful geometry, that something is wrong with its space, that the rules don't work the way they should, that space itself is curved. And here's the beautiful part. The bug does this without ever leaving its universe, without ever seeing it from the outside. The curvature is intrinsic. It's built into the fabric of space itself. Our universe might be exactly like that. We might be the bugs. Einstein told us that space is curved, not metaphorically, not as a mathematical trick, actually physically curved. The fabric of space, the void between stars, the emptiness you're sitting in right now, it bends. And what causes the bending? Mass, matter, energy. Every star curves space. Every planet curves space. Even you curve space, just a tiny bit. The more massive something is, the more it warps the space around it. So here's the picture. Our 3-dimensional space might curve in a 4th dimension that we can't perceive directly, just like the bug's 2-dimensional surface curves in the 3rd dimension. We can't see the curvature by looking at it, but we can detect it. We can measure it. And if our space curves enough, if it curves all the way around, then it closes on itself, like the surface of a sphere, but in 3 dimensions. What would that mean? It would mean the universe is finite. It has a definite size, a measurable volume. But it would also mean the universe has no edge, no boundary, no wall. If you got in a spaceship and flew in a perfectly straight line, just kept going and going for billions of years, you wouldn't hit a wall. You wouldn't fall off an edge. You wouldn't reach the end. You'd end up back where you started. Here's the truth. The universe might be finite, but unbounded. Limited, but edgeless. It might have a size, but no border. And this answers the question everyone asks, the question that keeps people up at night. What's outside the universe? Nothing. Not empty space, not darkness, not some other realm. Nothing. Because outside doesn't exist. Think about it. What's outside the bug's universe? What's outside the surface of the sphere? From the bug's perspective, the question makes no sense. The surface is everything. There is no outside. For us, it might be the same. Space-time is everything. There is no outside. The question assumes something that doesn't exist. And now comes the shock. This isn't just philosophy. This isn't just speculation. We can test it. We are testing it. Remember how the bug could detect curvature by measuring triangles and circles? We can do the same thing on a cosmic scale. We can look at the largest structures in the universe. We can measure the angles of giant triangles formed by distant galaxies. We can check if the geometry works out the way it should for flat space. And what do we find? So far, the universe looks very close to flat on large scales. Very close. But very close doesn't mean exactly flat. There could be a tiny curvature that we haven't detected yet. A slight curve that would only show up at scales larger than we can currently measure. If the universe is positively curved, like a sphere, then it's finite and closed. You travel far enough, you come back home. If the universe is negatively curved, like a saddle, then it's infinite and open. It goes on forever in every direction. If the universe is perfectly flat, then it's also infinite. Space just keeps going with no end. But here's what we know for certain. Whether the universe is finite or infinite, it doesn't have an edge. It doesn't have a wall. There's no boundary you can reach where space just stops. Either it goes on forever, or it wraps around on itself. Those are the options. Edge of the universe isn't one of them. Let me say that again, because it's important. Space doesn't end. Either it's infinite and keeps going, or it's finite and loops back. But there's no wall, no border, no end in the way your brain wants there to be. The universe is not a room. It's not a box. It's not contained inside something larger. The universe is everything, and outside is not a place. That outside might not exist. You might be wondering, okay, space is curved, but curved into what? If the bug's surface is curved in three-dimensional space, then our three-dimensional space must be curved in what? A fourth dimension? And here's where we have to be careful. We don't need a higher dimension for space to be curved. The curvature is intrinsic. It's a property of space itself, measurable from within, without reference to anything outside. Let me explain what I mean. When we say the bug's universe is curved, we're describing it from the outside. We see the ball. We see the surface wrapping around. But the bug doesn't see any of that. The bug just notices that geometry doesn't work right. Triangles are weird. Circles are weird. Something is off. The bug discovers curvature through measurement, not through seeing a higher dimension. We're in the same situation. We can measure the curvature of our space without needing to see it from a fourth dimension. We just do geometry on large scales and check if the results match flat geometry or not. Here's the key. Curvature is not about bending into something. Curvature is about geometry being different than expected. That's the definition. A curved space is a space where the rules of flat geometry don't apply. So stop trying to visualize the universe as a balloon floating in some larger space. That image is misleading. There's no larger space. There's just our space, with its own intrinsic geometry, which might be curved. Now, let's talk about something else. Because curvature isn't the only strange thing about space. Einstein told us something even more remarkable. Space and time are connected. They're woven together into a single fabric called space-time. And when we talk about the curvature of the universe, we're really talking about the curvature of space-time. This matters because it changes everything. Here's an example. You probably know that time passes at different rates depending on where you are. A clock on a mountain runs slightly faster than a clock in a valley. A clock on a speeding airplane runs slightly slower than a clock on the ground. These aren't mechanical errors. These aren't problems with the clocks. Time itself runs at different rates in different places. And why? Because of curvature. Mass curves space-time. And when space-time is curved, time flows differently in different locations. Think about what this means. Near a massive object like the Earth, space-time is curved. And that curvature affects not just space, but time. Clocks tick slower near massive objects. Time literally passes more slowly. This has been measured. This is not speculation. Scientists have taken identical atomic clocks, put one on a plane and one on the ground, flown the plane around, and compared the clocks afterward. They're different, by tiny amounts, but measurably different. The clock on the plane experienced slightly less time than the clock on the ground, because it was higher up, further from Earth's mass, in a region where space-time is less curved. But wait, there's more. This curvature of space-time isn't just an interesting fact, it's the explanation for gravity. You were probably taught that gravity is a force, that the Earth pulls on you, that there's some invisible rope connecting you to the planet, yanking you downward. But that's not what's happening. Here's the truth. You're not being pulled down. You're following the natural path through curved space-time. Let me try to make this intuitive. Imagine you're in a spaceship, far from any planet or star. No gravity. You're floating. Now the spaceship starts accelerating. It fires its engines and speeds up. What happens to you? You get pressed against the back of the ship. You feel weight. You feel exactly like you would if you were standing on a planet. Einstein realized something profound. There's no way to tell the difference. If you're in a closed box and you feel weight, you cannot determine whether you're on a planet being pulled by gravity or in a spaceship that's accelerating. The experiences are identical. This is called the principle of equivalence, and it's the foundation of everything. Here's why it matters. If acceleration and gravity feel the same, then maybe they are the same. Maybe gravity isn't a force at all. Maybe what we call gravity is actually the effect of curved space-time. Think about it this way. When you drop a ball, it falls. You think gravity is pulling it down, but actually, the ball is just following a straight line through curved space-time. That sounds crazy, right? How can falling be a straight line? Because in curved space-time, straight lines look curved from our perspective. The ball is taking the most natural path through space-time, the shortest path, the path that any free object would follow. We call these paths geodesics, and in flat space-time, geodesics are straight lines. But in curved space-time, geodesics look curved to us. They look like orbits, like falling, like the motion we associate with gravity. So the Earth isn't pulling you down. The Earth is curving the space-time around it. And you, by existing in that curved space-time, naturally move toward the Earth, not because of a force, but because of geometry. Now watch this. This explains something that puzzled scientists for centuries. Why do all objects fall at the same rate? A feather and a hammer in a vacuum hit the ground at the same time. Why? If gravity were a force, you'd expect heavier objects to experience more pull. But they also have more inertia, more resistance to acceleration. And these two effects exactly cancel. It seems like a coincidence, but in the curved space-time picture, it's not a coincidence at all. Objects aren't being pulled. They're following geodesics, and the geodesic doesn't care what the object is made of. A feather and a hammer follow the same curved path through space-time because the path is determined by the geometry, not by the object. Here's the secret. Gravity is not a force. Gravity is geometry. The curvature of space-time is what we experience as gravity. And this brings us back to the question of the universe. If mass curves space-time and the universe is full of mass, then the universe is full of curvature. Every star, every galaxy, every particle of matter contributes to the overall curvature of space-time. The total amount of matter and energy in the universe determines its overall shape, its geometry, whether it's curved like a sphere or curved like a saddle or perfectly flat. And that geometry determines the fate of the universe. If there's enough mass, space curves positively. The universe is closed. It's finite. And if you wait long enough, it might even collapse back on itself. A big crunch. If there's not enough mass, space curves negatively. The universe is open. It's infinite. It expands forever, getting colder and emptier. If there's exactly the right amount of mass, space is flat. The universe is infinite. It expands forever, but just barely, right on the edge between collapse and eternal expansion. Which one is our universe? We've measured it. We've looked at the cosmic background radiation, the leftover glow from the Big Bang. We've studied the distribution of galaxies. We've calculated the total mass and energy. And the answer is, our universe is very close to flat, remarkably close. So close that it's almost suspicious. But very close to flat leaves room for mystery. There could be a tiny curvature we haven't detected. And even if it is perfectly flat, the question remains, why? Why this particular geometry and not some other? Here's what we know for sure. Space is curved. Mass causes curvature. The geometry of the universe depends on what's in it. And that geometry determines whether the universe is finite or infinite, whether it has a shape that closes on itself or extends forever. The universe is not a fixed stage where things happen. The universe is a dynamic fabric that bends and warps and shapes itself according to its contents. And we're part of that fabric. We curve it, and it curves us. So let's bring this all together, because we've covered a lot of ground, and I want to make sure the picture is clear. Space is curved. The universe might be finite, but without edges. There's no outside. Gravity isn't a force, but geometry. Mass tells space-time how to curve, and curved space-time tells mass how to move. But there's one more thing we need to talk about, and it's the hardest part of all. Our intuition is wrong. Completely, fundamentally, hopelessly wrong about all of this. And that's okay. Here's why your brain struggles with these ideas. You evolved on a small planet, moving at slow speeds, experiencing weak gravity. Your ancestors needed to throw spears at animals, find ripe fruit, avoid predators. They did not need to understand the curvature of space-time. So your brain built a model of reality that works for everyday life. A model where space is flat, where time flows at the same rate everywhere, where things fall because they're pulled by invisible forces, where everything is contained inside something larger. That model is wrong, but it works well enough for surviving on Earth, so evolution kept it. The problem comes when you try to think about the cosmos, when you try to imagine the shape of the universe, when you ask questions like, what's outside? Your brain uses its everyday model and gets nonsense answers. Here's the truth. The universe is not required to make sense to your intuition. The universe is required to be consistent with itself. And it is. The mathematics works. The predictions match observations. The theory holds together. It just doesn't feel right. And that's your problem, not the universe's problem. Now, let me address something that might be bothering you. If the universe could be finite and without edges, if it curves back on itself, what does that actually mean for us? What difference does it make? Well, here's one way to think about it. Imagine you're an astronaut. You get in the most advanced spaceship ever built. You pick a direction and you start flying. Perfectly straight, no turns, just forward forever. In an infinite universe, you fly forever and never return. Every moment takes you somewhere new. Space goes on without end. But in a finite, curved universe, something strange happens. After billions of years of travel, the stars start to look familiar. The galaxies seem like ones you've passed before. And eventually, you arrive back at Earth, right where you started. You circumnavigated the universe without ever turning around, just by going straight. That's what it means for space to be curved and closed. Straight lines become loops. Forward forever becomes back to the beginning. Now, practically speaking, this doesn't matter much for our daily lives. The universe is so large that even if it's finite, it's far too big for us to ever circumnavigate. We'll never build a ship fast enough or live long enough to complete the journey. But conceptually, it changes everything. It means the universe doesn't need an outside. It doesn't need a container. It doesn't need edges or walls or boundaries. It can be complete in itself, self-contained. Everything that exists, existing within a structure that loops back and closes. Here's the key. The question, what's outside the universe, assumes a certain kind of universe. It assumes space is like a room, contained inside something larger. But if space curves back on itself, that assumption is wrong. There is no outside. The question dissolves. It's not that we don't know the answer. It's that the question doesn't apply.
You know what? People hate this answer. They really do. They want there to be an outside. They want there to be something more, something beyond. Their brains crave it. But the universe doesn't owe us satisfaction. The universe is what it is. And part of understanding physics is accepting that some questions are based on false premises. What's outside the universe might be one of those questions. Not a mystery we haven't solved yet, but a question that was never valid to begin with. Now watch this. There's something beautiful about this picture. Something I don't want you to miss. We are tiny, unimaginably small compared to the cosmos. We live on a speck of dust, orbiting an ordinary star in an ordinary galaxy among hundreds of billions of galaxies. And yet, we figured this out. We, the bugs on the surface, discovered that our space is curved. We measured the geometry, we tested the predictions, we built a theory that explains gravity as curvature and describes the shape of the universe itself. We can't see the curvature directly. We can't float up into a higher dimension and look down. But we deduced it through mathematics, through careful measurement, through the power of human thought. That's remarkable. That's genuinely miraculous. That creatures made of atoms can understand the fabric of space-time. That we can ask, what is the shape of everything, and actually make progress toward an answer. Let me leave you with something to think about. We don't know for certain if the universe is finite or infinite. We don't know if it curves back on itself or extends forever. The measurements are close to flat, but close isn't certain. What we do know
is that the universe is far stranger than our intuition suggests. The space bends, time stretches, geometry depends on what's in it. The cosmos might be a closed loop with no outside, or an infinite expanse with no end. Either way, there's no wall, no edge, no boundary where space stops and something else begins. The universe is infinite with an end, or finite without edges, or infinite without edges, but never, never a box with walls. Here's the deepest part. When you look up at the night sky, you're not looking at objects scattered inside a giant room. You're looking at matter embedded in curved space-time. Every star, every galaxy is part of the fabric, and the fabric shapes itself around its contents. The universe isn't a container holding things. The universe is the things, and the space between them, woven together, curving and flowing and existing as one unified structure. There is no outside, because there is nothing but the universe. It is complete, it is whole, it is everything. I know this is hard to accept. I know your brain wants more, wants an answer that fits into familiar categories, wants to know what's beyond. But sometimes the deepest understanding comes from accepting that certain questions don't have the kind of answers we expect, that reality is structured differently than we imagined, that the universe is under no obligation to make intuitive sense. So, what's outside the universe? Nothing. Not empty space, not darkness, not another universe. Nothing. Because outside is not a concept that applies. The universe might be finite, it might be infinite, but either way, it's everything, and everything doesn't have an outside. That's not a failure of knowledge, that's a feature of reality. That's how the cosmos actually is, and we figured that out. Tiny creatures on a tiny planet, looking up at the stars, doing geometry, testing predictions, pushing the boundaries of understanding. We can't see the curvature, but we know it's there. We can't visit the edge, but we know there isn't one. That's the power of physics. Not just collecting facts, but understanding the structure of reality itself. Understanding what questions make sense and what questions don't. Understanding that the universe is stranger and more beautiful than we ever imagined.
Ladies and gentlemen, let me start with a word we all think we understand: energy. We use it constantly. We drink it in cans. We complain about not having enough of it. We talk about good energy, bad energy, and saving energy. And yet, despite how familiar the word feels, energy is one of the most misunderstood ideas in all of science. Tonight, I want to do something very simple and very dangerous. I want to take that word away from you and then give it back in a form that actually makes sense. Here's the first thing you must accept. Energy is not a thing. You can't touch it, you can't see it, you can't put it in a box. If you try to imagine energy as a substance, some invisible fluid sloshing around the universe, you will be confused for the rest of your life. Energy is not stuff. Energy is a number, a bookkeeping number. And that fact alone already tells us something profound about how the universe works. Now, this sounds disappointing at first. A number, that's it? Yes and no, because this number has a remarkable property. It never changes. No matter what happens, collisions, explosions, chemical reactions, stars being born, stars dying, the total amount of energy stays the same, always, every time. The universe keeps perfect accounts. This principle is called the conservation of energy, and it is one of the deepest truths we know about nature. Not because we proved it, but because every experiment we've ever done has failed to contradict it. Nature could have chosen otherwise. It didn't. Now here's where things get interesting. If energy is just a number, what does it count? It counts the capacity for change. Anytime something happens, anything at all, energy is involved. Motion, heat, light, chemical reactions, life, thought. If something can cause something else to happen, energy is keeping score. Think of energy like money. Money isn't a thing either. It's an accounting system that tracks the ability to make changes in the world. You can store it, transfer it, convert it, waste it. But the money itself doesn't do anything. People do. Energy works the same way. Now let me ruin another comforting idea. Energy does not come in just one form. We give it names: kinetic energy, potential energy,
thermal energy, chemical energy, mass energy. But these are not different substances. They are different ways the same number appears, depending on the situation. Like the same amount of money appearing as cash, credit, or investments. Different forms, same total. Here's the rule the universe follows. Energy can change its form, but it cannot disappear, ever. When energy seems to vanish, it hasn't. It's just gone somewhere less useful, usually into heat, the universe's junk drawer. Now pause and think about this. Every machine ever built, every engine, every living organism, every civilization, all of it is about moving energy from one form to another. Life itself is not about creating energy, it's about channeling it cleverly. And here's the twist most people miss. Energy is not conserved because of some mechanical rule. It's conserved because the laws of physics do not change with time. The universe today follows the same rules it did yesterday. That symmetry, time behaving consistently, is what protects energy. Energy conservation is not just a rule, it's a consequence of order. This means something extraordinary. If tomorrow the laws of physics change slightly, energy would no longer be conserved. The universe would become unpredictable, chaotic, unrecognizable. The fact that energy is conserved tells us that reality has a deep underlying stability. But now we must confront the most unsettling idea of all. If energy is always conserved, and everything that happens uses energy, where did it all come from? And even more troubling, what does it mean that you are part of that accounting system? To answer that properly, we need a concrete handle, something ordinary, familiar, almost boring, because energy only becomes confusing when we talk about it abstractly. When we watch it work, the mystery sharpens. So, let's start with a machine so simple it feels harmless. Imagine a pendulum, a weight on a string. You lift it, let it go, and it swings back and forth. Nothing dramatic, no smoke, no sparks, no equations carved into stone tablets. Now here's the question your intuition answers instantly and incorrectly. You look at the pendulum and think. At the top, it has potential energy. At the bottom, it has kinetic energy. They trade places. That story feels satisfying. It feels like something is moving around inside the pendulum, but nothing is moving except the pendulum itself. The energy isn't hiding somewhere, waiting its turn. There is no little packet labeled potential that jumps into a packet labeled kinetic. What's actually happening is much stranger. At the top of the swing, the pendulum is arranged in a way that could cause motion. At the bottom, it is arranged in a way that is motion. Energy isn't a thing passing back and forth. Energy is a number that stays the same while the description changes. Same system, same total, different bookkeeping. Now let's push this further, because common sense is still clinging on. If energy is conserved so perfectly, the pendulum should swing forever. But it doesn't. It slows. It stops. Eventually it just hangs there doing nothing. So where did the energy go? You already know the answer. Friction, air resistance, heat. But notice what your intuition tries to sneak in. It imagines energy leaking out like water from a cracked pipe. That's wrong. Nothing leaked. The energy is still there, just spread out among too many atoms to be useful anymore. The air warmed slightly. The pivot warmed slightly. The earth warmed slightly. The universe noticed. You didn't. This is the moment where common sense fails most dramatically, because common sense equates not useful with gone. Physics does not. Physics only asks one question: can I still account for it? And the answer is always yes. This was made brutally clear in a famous 19th century experiment by James Joule. Joule took a container of water, dropped weights that turned paddles inside it, and measured the temperature increase.
Mechanical motion turned into heat, not metaphorically, not symbolically, quantitatively. Drop the weights twice as far, the water heats twice as much. Every time, no exceptions. Energy didn't vanish, it changed what it was doing. This is the core mechanism you must understand. Energy does not care what it looks like, it only cares that the total is preserved. Motion, heat, light, chemical bonds, electrical currents, these are not different substances, they are different languages describing the same constraint. Now let's challenge intuition directly. You feel tired. You say, "I'm out of energy." But that's false. You are full of energy. What you lack is accessible energy in a useful form. Your body is a chemical engine. It runs by converting tightly packed chemical energy into motion, heat, and electrical signals. When that conversion becomes inefficient, you feel exhausted, not because energy is gone, but because it's trapped in forms your muscles can't use quickly. The universe didn't take anything from you, it just made conversion harder. This is why engines matter so much in physics. A steam engine, a car engine, a cell, these are not energy creators, they are energy translators. And translation is never perfect. Some meaning is always lost. Some energy always ends up as heat. That's not poor engineering, that's reality. Here's the analogy that usually snaps things into focus. Imagine energy as money, but money that can only be spent in certain stores. You might be incredibly wealthy, but if all your money is locked in a currency no one accepts, you're powerless. Energy works the same way. The universe accepts fewer and fewer currencies over time. And now comes the realization that unsettles people. The conservation of energy is not about motion or machines. It's about consistency. The universe does not change the rules halfway through the calculation. If you run an experiment today or 1 billion years ago, the accounting balances the same way. Energy conservation is not enforced by a cosmic police officer. It happens because the laws of physics are stable in time. If the rules drifted, even slightly, energy would not be conserved, and neither would anything else you rely on.
So when common sense says energy makes things happen, physics quietly corrects it. Energy does not cause change. Energy measures the capacity for change under fixed rules. The rules come first. Energy keeps score. This is why energy feels so fundamental. It's not because it's a substance beneath everything. It's because every possible change must respect it. No loopholes, no exceptions, no negotiations. And that brings us back to you. You don't sit outside this process observing energy flow through the universe. You are one of the allowed pathways energy discovered, a pattern that holds for now. And once you see that, once you really accept that energy is not a thing, but a rule you can't cheat, something subtle happens. The universe starts to look less like a collection of objects and more like a collection of allowed changes. Because energy doesn't tell matter what to do, it tells matter what it is not allowed to do. You can rearrange endlessly, but you must always balance the books. This has consequences that reach far beyond engines and machines. For example, motion. We tend to think of motion as primary, as something basic, things just move. But motion turns out to be negotiable. You can always change your point of view and make a moving object look still. You can ride alongside it. You can redefine your frame. Energy doesn't care. The energy accounting works in every frame, every perspective. That's already a hint that energy is deeper than motion itself. Now let's talk about forces. Forces feel real. You feel gravity. You feel a push. You feel resistance. But forces are not fundamental in the way we instinctively think. A force is just a way of describing how energy changes with position. That's it. If energy depends on where something is,
It experiences a force. No mystery, no hidden hands, just bookkeeping again. The universe doesn't push things, it follows gradients in energy. This quietly unifies an enormous amount of physics, gravity, electricity, magnetism, even the forces inside atoms. They all emerge from the same idea, energy arranged differently in space and time. Once you see that, the laws of physics stop looking like a random list of rules and start looking like variations on a single theme. Now here's where the surprise enters. If energy is always conserved, and if it controls what changes are allowed, then energy places limits on reality, absolute limits. You cannot build a perpetual motion machine. You cannot extract infinite work. You cannot rewind the universe to yesterday, not because we lack cleverness, but because the rules don't allow it. This is where physics becomes philosophical, not by adding speculation, but by refusing to. The universe is not just what happens, it is what is permitted to happen, and energy is one of the strictest permissions we know. This brings us to a paradox people often stumble over. If energy is conserved so perfectly, how can anything genuinely new ever occur? How can novelty exist if the total never changes? It feels like a contradiction, but it isn't, because novelty doesn't come from new energy. It comes from new arrangements. The alphabet is finite. The number of books is not. This is why complexity is possible. Stars, planets, life, minds, none of these required extra energy to appear. They required pathways, sequences of transformations that happened to hold together long enough to build structure. Energy didn't create complexity. Energy allowed complexity. And now let's confront something even more unsettling. If energy accounting governs everything, then causality itself is constrained by it. You can't get an effect without paying the energy cost. You can't get information without dissipation. You can't think without burning fuel. Every thought you've ever had has a thermodynamic footprint. Meaning is not free. Understanding is not free. Awareness is not free. They all cost energy. This doesn't diminish them, it grounds them. It tells us that meaning is not an exception to the universe, it's one of its natural outcomes. At this point, people often ask, so is energy the most fundamental thing? And the honest answer, the only respectable answer is, we don't know. Energy may be fundamental, or it may be a shadow of something deeper, the way temperature is a shadow of molecular motion. What we do know is this: any deeper theory we find must still explain why energy accounting works so perfectly, because reality refuses to let us escape it. And notice something remarkable. We never defined energy by what it is. We defined it by what it does. It constrains, it balances, it limits, it connects. Energy is less like a substance and more like a promise the universe never breaks. This changes the meaning of understanding. To understand something deeply in physics is not to imagine it vividly. It is to know what cannot happen, no matter how much you want it to. That's real knowledge. So when you ask what energy means, the answer is not poetic, but it is profound. Energy means the universe is consistent. Change is possible, but not arbitrary. Complexity can arise without miracles, and nothing gets a free pass. So now we can finally assemble the whole picture, not as a collection of clever ideas, but as a single working view of the world. Energy, at the deepest level we currently understand, is not a material ingredient added to the universe. It is a constraint on change. It is the quantity that must remain constant, no matter how wildly the universe rearranges itself. Every law we trust, every equation that survives experiment, respects that constraint. This already tells us something concrete and non-negotiable. The universe is not free to do just anything. If a process violates energy conservation, it does not merely seem unlikely, it does not exist. Full stop. This is why physicists take energy conservation more seriously than almost any other principle. Entire theories have been discarded, not because they were inelegant, but because they failed to conserve energy. Even relativity and quantum mechanics, radical as they are, were built to preserve it, not replace it. We also know something very specific about why energy is conserved. In modern physics, conservation of energy arises from a deep symmetry. The laws of physics do not change with time. An experiment performed today will behave the same way tomorrow or a billion years from now. That temporal stability is not an assumption. It's an observed fact, tested constantly. If the laws of physics drifted even slightly with time, energy would not be conserved. The universe would gain or lose energy without explanation. The fact that this does not happen tells us that time itself has a remarkable uniformity built into it. That is not philosophy. That is measurement. Now let's be precise about what energy actually tracks. Energy is not a cause. It is not a force. It is not an agent. Energy is a scalar quantity that assigns a value to the state of a system. That value determines which changes are allowed and which are forbidden. Systems naturally evolve toward states where energy is more evenly distributed, because those states are overwhelmingly more probable. This is why heat flows from hot to cold, why friction exists, why engines have efficiency limits, why time has a direction. Not because the universe prefers disorder, but because there are simply more ways for energy to be spread out than concentrated. We also know something else that matters enormously. Energy conservation does not mean nothing truly happens. It means nothing happens for free. Every increase in structure requires energy to be concentrated somewhere, and that concentration must be paid for by dispersing energy elsewhere. This is why every act of creation is also an act of waste. Every star, every organism, every idea is accompanied by heat leaking into the surrounding universe. Life does not violate this rule. Life survives because it obeys it more cleverly than its surroundings. Now, what don't we know? We do not know why the universe began in a state where energy gradients existed at all. We do not know why there was something like usable energy instead of a perfectly uniform, inert equilibrium. We do not yet know whether total energy of the universe is exactly zero, positive, or even definable in a simple way at cosmic scales. We also do not know whether energy is truly fundamental, or whether it emerges from a deeper description, perhaps one based on information, geometry, or quantum structure. These are open questions, real ones, active ones. Energy conservation is not the final word. It is the rule that every deeper theory must still explain. And now, here is the synthesis that matters. Energy tells us that the universe is not arbitrary. It is constrained, consistent, and legible. It tells us that change is possible, but only along permitted paths. It tells us why complexity can arise without miracles, and why permanence is never guaranteed. And most importantly, it tells us something about our place in the story. You are not an exception to physics. You are not outside its accounting. Your metabolism, your memory, your thinking, all are physical processes with measurable energy costs. Thought consumes fuel. Learning leaves thermodynamic traces. Meaning requires work. That does not reduce human experience. It anchors it. The final takeaway is not that energy explains everything. It's that energy explains why explanations work. Because the universe keeps its books honestly, patterns can persist, laws can be discovered, and understanding can multiply. Without that consistency, science itself would be impossible. Energy is the quiet agreement reality makes with itself. Change is allowed. but it must balance. And because of that agreement, there is motion, time, life, curiosity, and the universe capable of being understood at all.
Every time you seek approval, your worth becomes a hostage to someone else's opinion. And the strange thing is, the more you try to please the world, the more the world ignores you. Life begins to lose its brightness when you live to be seen instead of living to understand. Now imagine just for a moment that all the energy you spend trying to be accepted was redirected into learning, into exploring, into understanding how things truly work. Imagine the power that would have. You'd start to see the hidden beauty in simple things, in sound, in light, in ideas, in people. Because true genius isn't born from the desire to be admired, but from curiosity. That pure restlessness that makes you want to discover why things are the way they are. And when you dive into that curiosity, life starts to flow in a way that no ambition can ever reproduce. The truth is, the pursuit of recognition is a trap disguised as motivation. It pushes you to run faster, to work harder, to achieve more, yet it never lets you rest. It's a bottomless pit. And you know what's at the bottom of that pit? Nothing but emptiness. The emptiness of someone who lived to be remembered instead of living to understand. So listen closely. Living for the love of understanding is the only path that truly sets you free. Because the pleasure of discovering is the reward itself. And the one who learns for the joy of learning never needs applause. Pay attention to me now, because what I'm about to tell you might completely change the way you see life. You've spent far too long trying to be recognized, trying to prove something to others. And without realizing it, you became a prisoner of that need. But let me tell you this, most of the people who seem to be winning are actually losing silently. They collect titles, possessions, praise, yet they lose something invisible, their inner freedom. They live like actors on a stage, playing a role the world wrote for them. But you know the problem? When the curtain falls, there's only silence. And in that silence, the question no one wants to face appears. Why am I doing all this? If your reason is to be recognized, you'll never rest. Because recognition is volatile. It shifts with people's moods, with trends, with the tides. One day they applaud you, the next they forget you. And if your worth depends on that, you're doomed to rise and fall with the world around you. But when you do something for the simple joy of understanding, something inside you changes. Suddenly time moves differently. You stop chasing, and you start being guided by something deeper. Curiosity. Curiosity is the engine of life. It turns boredom into discovery, pain into learning, chaos into meaning. When you follow that energy, you no longer need recognition, because the pursuit itself becomes fulfilling. It's the joy of understanding what lies behind things, of seeing how everything connects. That is true power. When you learn for the love of comprehension, the entire world opens before you. You stop being an actor, and you become the author. And for the first time, life starts to make sense. But to reach that point, you must do something few ever dare. Stop trying to be someone, and start trying to understand something. The difference seems small, but it's enormous. The first path enslaves you. The second one sets you free. Pay attention to me now, because I want to take you to a place where very few have the courage to look. People think freedom means being able to do whatever they want, but that's just the reflection of modern ignorance. True freedom is being able to think whatever you want, to doubt what you've been taught, and to allow yourself not to know. A mind that seeks recognition is enslaved by certainty. A mind that seeks understanding is free to explore. Do you want to know what truly destroys genius? The need to appear intelligent. The person who tries to look smart for others will never be truly intelligent, because they're focused on displaying, not discovering. Genius is born the moment you abandon the desire to be special and embrace the joy of uncovering the obvious. Think about it. Everything you know was once obvious to someone who had the courage to look closely. The difference between the mediocre and the brilliant doesn't lie in talent. It lies in genuine curiosity. The mediocre wants to be right. The brilliant wants to learn, even if it means stripping away their own vanity. And here's the irony. The more you care about what others think, the less you actually think for yourself. A curious mind is like a child taking apart a toy just to see what's inside.
It doesn't crave status. It doesn't want applause. It wants the mystery. It wants the why. And that's what keeps the inner fire alive. The sincere desire to understand the world before the world understands you. Life becomes light when you realize you don't need to impress anyone. You begin to do things for the simple pleasure of seeing what happens. And strangely enough, that's when everything starts to work. When you stop chasing results, the results begin to chase you. Because the universe responds to genuine curiosity, not to empty ambition. The secret isn't to be recognized, it's to be so deeply immersed in the process that recognition becomes irrelevant. The reward lies in the very act of understanding. And those who live that way exist in a state of freedom that money and status could never buy. Now imagine something uncomfortable yet necessary. What if most of human suffering didn't come from lack, but from excess? The excess of wanting, proving, showing. The world taught you that ambition is a virtue, but forgot to warn you that blind ambition is poison. You run, you exhaust yourself, you achieve, and when you finally arrive where you always wanted to be, you realize there's no one there, not even you. People confuse purpose with performance. They crave meaning, yet spend their days trying to win a race they never chose to run. They long for freedom, yet choose paths that chain them. The pursuit of status, applause, validation. And the worst part? They believe they're evolving, when in truth, they're only moving further away from themselves. Let me tell you something few have the courage to face. Success without understanding is just another form of failure. Because if you don't understand what you're doing, success becomes an accident. And accidents don't set you free. They enslave you. When you act only for the result becomes your master. But when you act for the love of understanding, you are in control, and life begins to flow again. There is no purer pleasure than the pleasure of truly understanding. When you truly understand, there's no need to compete. There's no envy, no rush, no comparison. There's only a curious silence, that rare moment when everything makes sense for just a few seconds, and you feel part of something far greater than ambition itself. The problem is most people want to understand the world, but they don't want to understand themselves. They crave answers but can't stand questions. And that's why they live tired, anxious, and empty, because they try to fill what is spiritual with what is material. They try to buy, conquer, or prove what can only be understood. Life is not a podium. It's a laboratory. You're not here to win. You're here to discover. And when you understand that, you realize the whole game changes. It stops being a competition and becomes an investigation. Every mistake becomes a clue. Every failure, a new hypothesis. And that's how you begin to free yourself. Not by winning, but by understanding. When a human being finally lets go of the need for recognition, something extraordinary happens. They are reborn. The mind becomes light. The heart becomes quiet. And for the first time, they begin to taste real freedom. Suddenly, fear disappears. The fear of failing, of being judged, of not being enough. Because now, none of that matters. You no longer live to prove. You live to experience. And in that moment, life starts to align with who you truly are. Opportunities appear. Ideas flow. The right people come closer. Because you stopped being a copy begging for acceptance and become an authentic source of energy and creation. Authenticity has a power the modern world has forgotten. When you are real, the entire universe seems to recognize you in a way applause never could. Life begins to conspire in your favor, because at last you're playing the right game, the game of growing from within. And everything that once seemed difficult begins to happen naturally, because when your focus shifts from appearing to understanding, you connect to the natural flow of things. You don't force, you simply are. Do you want to know what true peace feels like? It's waking up one day and realizing you don't need to impress anyone, that you are enough simply for being here, learning, failing, trying to understand. And from that moment on, every gesture, every word, every small discovery starts to have meaning. You begin to see beauty where you once saw routine. You begin to see purpose where you once saw haste. Lightness is born when vanity dies. And the pleasure of discovery becomes greater than any achievement. Life flows, not because you control it, but because you understand it. And once you understand, you no longer need to run. You realize that what truly matters is not what others think of you, but what the universe reveals when you finally choose to listen. Now write this in the comments. With conviction, I choose the freedom of understanding. This phrase will begin to reprogram your subconscious, reminding your mind every day of what truly matters. From today on, make yourself a promise. Live for the love of understanding, not for ambition. Stop chasing recognition and start seeking meaning. That is the key that changes everything. If this message touched you, like the video, subscribe to the channel, and turn on the bell because what's coming next will expand your mind even more. And remember, to understand is to be free, and the one who becomes free inspires the world without needing to say a single